In this video, we're going to learn about gas stoichiometry. Now, the first thing you need to know about gas stoichiometry is that at standard temperature and pressure, 0 degrees Celsius and 1 atmosphere, 1 mole of any gas occupies a volume of 22.4 liters. So if we're given the problem, 2.00 moles of KClO3 are heated to decomposition according to this chemical equation, and the oxygen is collected at STP. What is the volume of the oxygen collected? What we do is, well, we start off with our 2 moles of KClO3. We know we're trying to find the volume of O2. And to go from one substance to the next substance, we need to use moles as our bridge. So we go from moles of KClO3 to moles of O2, and then from there we go to liters of O2. This is kind of similar to going between grams and moles in the case of a solid. The difference is that in the case of grams to moles, we need to use molar mass, and that requires looking up elements on the periodic table. In the case of gases, it's always the same. Doesn't matter whether it's oxygen or hydrogen or anything else. That molar volume at STP is going to be 22.4 liters per mole. So we'll finish setting this up. I know that I'm going to use my mole ratio of 3O2 to 2 KClO3 to get to moles of O2. And then I just use the molar volume to get to liters of O2. Setting this up, we have 2 moles of KClO3 times that mole ratio of 3 to 2 times the molar volume gives us 67.2 liters of oxygen produced. So that's at STP, but when we're not at STP, then we need to use the ideal gas law, and here's an example. We have the same chemical equation here, but this time we're given 12.3 grams of KClO3 just to make it a little bit different. And in this case, we find that the oxygen collected is collected at a temperature of 673 Kelvin. So we are not at standard temperature and pressure. Pressure is standard, I guess, but the temperature is not. So if we're asked to find the volume of the oxygen collected, we can set this up according to what we have. We know we've got the grams of KClO3. We need to go to liters of O2. And to do that, we need to first get moles of KClO3 and then moles of O2 and then liters of O2. The conversion factors, well, we need to use the molar mass of KClO3, which is 1 potassium plus 1 chlorine plus 3 oxygens. Look their molar masses up on the periodic table and add them, and you get 122.55 grams per mole. Then we multiply by 3 moles of O2 for every 2 moles of KClO3. And the final bridge to get between moles of oxygen and liters of oxygen is PV equals nRT. More on that in a minute. What I'm going to do is I'm going to set up the dimensional analysis, cancel out the grams, cancel out the moles, and what I'm going to do is stop at moles of KClO3. And the reason I'm doing that is if I want to use PV equals nRT, it's going to be very difficult to integrate this into the whole dimensional analysis that I have here. But what I can do is say, all right, for my PV equals nRT, I know the pressure is 1 atmosphere. The volume is what I'm trying to find. So I'll keep that circled. The N is my 0.151 moles of oxygen. R is the gas constant, and my temperature is the 673 Kelvin. So actually, I'm all set to do PV equals nRT. I'm going to rearrange that to solve for the unknown, V. So V equals nRT divided by P, if I divided both sides by the pressure. And if I just substitute in the variables as I know them, again, moles times gas constant times temperature divided by the pressure is equal to the volume. What I end up with is that the volume is 8.34 liters. And that's how you would use the ideal gas law to solve problems involving gas stoichiometry at non-STP conditions. Hope the video has helped. Feel free to leave any questions or comments in the comment section below. Thanks for watching.